bad. What? Oh, okay. I think we're live now. Just give me a thumbs up if you see it. Yep. Okay. We're live. Hello, everyone. Welcome to the 5th stream of the GameDev office hours. Today, we'll be talking about FBX and how to export geometry or animations, pack primitives from Houdini to game engine. Once again, using FBX. The game engine of choice we'll be using today is Unreal Engine 4, because we've seen most of the requests or questions about how to do this for Unreal. But that doesn't mean that what I'm showing you today isn't applicable to other game engines, such as Unity or even proprietary game engines that support the import of FBX format. So I'll be showing you a couple of scenarios today of things that people might want to do with exporting FBX. The most obvious one, of course, is just a static export, which is just a piece of geometry, right? A static mesh. Export a single frame and import that into, Unreal. I'll be showing you UVs, vertex colors, materials. I'll also be showing you how you can export an FBX with sub-meshes in it. So, for example, if you have a bunch of boxes, instead of Houdini exporting it as a merged piece of geometry of, let's say, 10 boxes, I'll show you how to export it as 10 separate boxes. I'll also be showing you RBD to FBX. So if you've done, a really cool RBD sim in Houdini, how can I export that as a bone-based animation to Unreal or any other engine? So we'll be showing the RBD to FBX tool. I'll also be showing Pivot Painter. I received quite a few questions about how to properly import Pivot Painter geometry into Unreal. So I'll be showing you all the right import settings, which are also listed on the tutorial page. And then last but not least, we'll be showing you how to export animated geometry as well for example, characters, or in this case, the example I'll be using the skinning converter. So to start with, the static export. Okay, so I'll just go to open and go to my live stream folder, and we'll be going to static export and open that. So just to show it as a tutorial kind of thing, I'll be using the rubber toy because the geometry doesn't really matter. This could have been a building, it could have been anything that you make in Houdini, as long as it's not animated, okay, for this example. So to begin with, before we add any attributes and so forth, I just want to show you how do we get this out into a game engine using FBX. The most easy solution you can do is just type FBX here in SOPs, right? Click tab and type FBX, and you'll get this node called ROP FBX, which is essentially just a wrapper of the FBX Filmbox ROP that we have in the ROP context. So just wire that in, and then we can set the frame range. In this case, since we're in SOPs and we can't export any point-based animations or vertex-based animations, set this to current frame. For the output file, I'll just keep it as hip/out, so it will export an FBX with the name out in the same directory my hip is saved in. And then all of these other settings, they don't really matter too much for a static piece of geometry, because there's no, no skinning weights, no end effectors, no bones there. The only two things that you might want to play with is disable export in ASCII format. So if you want to export it in binary format, which will reduce the file size of your FBX, then you can deactivate this. But if you want to be able to manually open the file in, let's say, WordPad to fix a problem or see where it was exported from without having to import it into an application like Houdini or Unreal, text-based format might be better. And then also, depending on what kind of importer you have in your, for example, proprietary engine, you can also change the FBX SDK version. But the default one, which is the one that Houdini is already set to, is usually fine. Then all you need to do is just hit save to disk, and that is going to export our piece of geometry here, right? So there we have our out object. So let's open up Unreal and create a new scene, new level, default. Oh, I think Unreal crashed. Let's just boot up a new instance of Unreal. Oh, there we go, it crashed. Oh, no, it's still working. Awesome. Once again, reminder, it's a live stream, so things like these happen, but that also means that it's interactive. So if you have any questions that you might want to ask during the stream, feel free to interrupt us and we'll answer those directly. I think the stream was hanging for a bit, but that should be resolved already. Let me just confirm. All right, so we were going to import our FBX. So we have our file here, and what we can do is we can just click and drag that into the content browser, and that is going to give us this FBX import options dialog. So to make sure that everyone's on the same page, I'm going to click revert to defaults, and that is going to reset all of the settings to the default settings inside of Unreal. These default settings might be different for you based on which engine version you're using. The version that I'm using is 4.22. The option I like to set by default is the vertex color import option. Set that to replace, because otherwise, if you, for example, update your vertex colors and you re-import your geometry, your vertex colors will not update properly. The other important setting for you when you're importing from Houdini is the convert scene toggle. So if you enable this toggle, it will automatically convert the Houdini coordinate system to the Unreal Engine 4 coordinate system. So if you were to disable this, you'll see that your geometry might be flipped in a different orientation. If we enable this, we will get the proper Z up, which is the coordinate system that Unreal has. We can see the little gizmo here. The other thing is the import scale. Unreal uses 1 unit equals 1 centimeter, while Houdini uses 1 unit equals 1 meter by default. So to get the same look and same size between these two applications, we need to multiply our meters by 100, right? Because we're going from meters to centimeters, which is a difference of 100. So if we import that and click import, it will import our FBX and give it to us here in the content browser. There we go. Unreal seems to be a bit slow today. I don't know why. Maybe my computer is out of resources. And there we go. We have our rubber toy inside of Unreal already. So that was pretty easy. We can also see that we also have our material slot, because if we go here inside of Houdini and click on spreadsheet, we can see that under primitives, we have an attribute called shop material path. And for every single unique value of shop material path, we'll get a unique material slot for our geometry. So if you, for example, wanted to have 2 material slots on our geometry, for example, a different material for the legs or the arms of the rubber toy, then we can, for example, use SOP quick material. Okay, this allows us to very easily create multiple materials. So I'm just going to create 2 materials. The first one will color, for example, red. Let's set this to 3D connectivity. This window, by the way, you can enable by clicking the 9 key on your keyboard. That allows you to, for example, say, I want to make selections based on 3D connectivity. So I'll select that, hit enter, and then, for example, we'll make this guy red. And then the other one, we'll select this guy here. we'll make this guy green. There we go. So now if we click on our spreadsheet once again, oh, I don't know what's going on. My mouse is acting up. Spreadsheet. Now we can see that we have at least 3 different shaders attached to it, right? Or 3 different values. I need to stop presenting here to increase bandwidth. Okay, hope that improves the quality. And then once again, we can export it out. Let's just change this to out2 and hit save to disk. Okay. Then let's take out2 and once again import that into Unreal. We'll get the same import dialog. We can just hit import because it remembered the same settings from the previous import we did. I don't know what's going on, why it's so slow. Let me boot up a new instance. Let's try 4.19. There we go, see, Unreal crashed. Are there any questions in the meanwhile, Mike?
No, I think we're just trying to sort out technical difficulties at the moment.
Okay. Let me just disable video as well. Might improve quality. Unreal still booting up.
Okay, hopefully we've fixed some of this. I'm streaming.
Can you guys hear me?
Yeah. Okay. So I think we're back. So we're just switching around streams here.
Yeah,
Sorry about this,
like
guys.
You're still showing your screen.
Yeah, I pressed stop already, so that's probably
that's
delay.
This is on my side. So yeah, Paul, you're good to go. So if you can,
we're still live right now. This is going on right now.
This is happening. So Paul, if you're good to go, you can share your screen through Meet, and we can carry on.
Okay, so I think we're back. All right, just let me know as soon as you see my Unreal screen again.
Yeah, it's up there. Yeah, it's up there. You're streaming, Paul.
Yeah. Okay. Yeah. So let's continue with our stream. I'm just putting up Houdini right now. Wait for that to finish. Okay. Let's make this attempt number 2. Live stream, FPX export, static export. Okay, so we should be good to go now. Let me just create a new level so that we don't have any of the overhead of the other stuff. It also seems that Unreal behaves a lot better now, so a quick reboot of my computer helped out a lot. So just a reminder for everyone. Import our geometry. So what I did before the stream crashed is create a couple of material slots on the rubber toy, which meant that we had several unique values of the shop material path on our primitives. And once again, every single unique value will create a new material slot in our FBX file. So let's open our scene back up here in Houdini as well. Static export. There we go. Let's see if Unreal wants to import it today. Seems like it does not. Okay, there we go. We have our file. Let's scale this up by 100. We can also do this in the import dialog. But the thing that is the most important, at least what I wanted to show, is we now have a couple unique material slots. So those are the ones that we applied inside of Houdini. So if we, for example, created a couple of materials here, oops. Oh, it's called vector here. There we go. And we plug it into our base color. And let's, for example, make this red and hit apply. Hit save. And assign this to one of our slots. We can now see that we indeed get that material slot on our legs. Next up, let's increase the difficulty a bit, or at least add some more interesting stuff, is UVs. So by default, our rubber toy already has UV channels. So UV without anything will be our texture UVs. And as you can see, we have a world grid that looks pretty nice, which means that our UVs are fine. So if we double click on our static geometry and enable the UV window, we can see that we do indeed have those UVs that we had inside of Houdini. Now, if we wanted to, for example, create some more UVs, we could just do create another attribute value called UV1, and that would be the light map UVs for our geometry. Okay, I'll show that later on with Pivot Painter, because Pivot Painter essentially takes all these attributes and uses them for something. I do, however, want to show you vertex colors. So to create vertex colors, really easy. Those are basically just point colors like you have in Houdini. Let's set this to vertex and say bounding box. Now, if we disable our material, we can see that we added vertex colors, or CD, to our vertex attributes, and that is the colors we see here. Okay. So once again, let's create an FBX export sub and call this out3. Hit save to disk. Open up Unreal again and drag this guy in here. Let's set that. That's all right. Import it. wait for it to import once again. Still importing. Well, while Unreal is thinking, I'll start with the next example inside of Houdini. So the next example I want to show you is the packed primitive export. Okay, and for that I'm just going to create a new file, and I'm going to save that as packed prim. Okay, so we have our packed prims, and the first thing to know is to create geometry in Houdini, we can, for example, type box. Okay, so if you were to export this as an FBX, which we can also do through the file window, we can say export film, then we can set our export path here, select which object we want to export here. That's one way of doing it. But what if we want to use the procedural power of Houdini to create 10 boxes and export those all at once? Well, one way of doing it is creating a box, duplicating it, and moving the translate value. Right? We can do that 10 times and export that out, and that will give us 3 separate boxes inside of Unreal, right? So let's just make a subnet and we'll export that in a minute. However, those are quite a few steps, right? So what if we can simplify that process a bit by just creating a geometry node and then creating a box and then using a good old copy and transform node. Now we don't have to manually copy our boxes. We're just going to say translate my box this much, and I want to have, let's say, 10 copies of that, right? So now we have 10 boxes. If we were to, once again, use the same trick we did before by using this FBX ROP SOP, then this would give us one mesh. But that's not what we want. We want to have 10 separate objects. Let's see. Okay, this is done. So what we'll do is break these up into separate objects. And for that, we can use the static fracture export node. We just drop this node down and plug it in our geometry in SOP land, and then we'll see this interface here. We can say which frame we want to export, which container name we want. So that is going to be the name of the subnet it is going to generate for us. And export mode, packed primitives, or piece attribute. So there's 2 types of data that static fracture export can use to separate the boxes into separate objects, one of which is packed primitives. For that, we can use an assemble SOP and then enable create packed geometry. And this will give us 10 packed fragments because we have 10 boxes and they're not connected by any geometry in between them. The other way is using an attribute, like for example class or name. So if we were to go into our spreadsheet and look at the different name attributes that it generated, we can also see that we have 10 different values. Another way to visualize this is by clicking the node info button here and clicking on the attribute that you want to visualize. So if I click that, we can now see that we do indeed have 10 unique values, illustrating that we have 10 unique values, which is also what this information says here. So to disable it, click the name again, or disable your visualizers here. Next up, on our SOP static fracture export, set this to piece attribute, because I'm going to use that name attribute that we saw before, and then just hit static export. And that for us will create this subnet mimicking the behavior that we had before, right? So instead of manually copying all these boxes or extracting them, static fracture export does that for us automatically. So let's delete this guy and prove that these indeed are 10 different objects. So as we can see, if we click the display flag or deactivate it, we can see that those indeed are 10 unique. So to export this, we can either go here in the ROP context and say FBX. And then in here, we can say where we want to export it in a single frame and what object we want to export. And I'm not going to point to any of these objects because we want to export all of them, right? We want it to be a container holding 10 separate sub-meshes. So to export them as separate objects, click the subnet, which says fracture container or whatever name you had. Then we can keep all these other settings the same and just hit save to disk once again. And that will give us our geometry. There we go, we have our FBX file. Let's delete this guy and delete these guys. We don't need those anymore. And once again, drag and drop our geometry into the content browser. So previously you saw I was scaling up the objects by 100 in here, but once again, we can also do this here with the import uniform scale. Another way of doing it, it seems like Unreal is a lot faster now. Another way of doing it is, of course, scaling up your geometry inside of Houdini before exporting it, right? So we'd go in here, right? So we'd go in here and set this scale to 100. That would also work for us because now we can see that we're dealing with a lot larger units. So instead of this being 625 meters, this would be 6.25 meters instead. And there we go. We do indeed have our 10 objects. So if we select all of those and import them in, we now have separate pieces of geometry, as you can see if we click on them. You can ignore these invalid light map settings. That's just because I don't have any UVs on these boxes. Okay. But yeah, that's a great way of exporting these out. Great for example, if you have lots of foliage that you scattered on a grid and you want to export all of those plans separately through FBX, then that is a way of doing it. The next example is, oh, I need to stop sharing and share again. The next example is the, in principle, the same. We're going to export all of these separate objects, but those are going to be animated. Oh, let me just restart this. Okay, and Mike was kind enough to create an example for me to use today. So I'm going to click on RBD export, and this is the file that Mike made for me today. So we can throw away this other scene. We don't need that anymore. And just load that up here in Houdini. And this is an example that you might have seen before. Mike used this for the RBD director and the other great tools that he made. But what we essentially have is just an animation, which was done in DOPS using Bullet. So if we middle mouse on our node here, we can see that we have 205 packed fragments, and those all have animation on them. So if we were to click visualize points and go into in wireframe mode, we'll see that the animation is not stored on the individual points or vertices of these pieces of geometry, but they're stored as transforms in the primitive intrinsics. What are primitive intrinsics? Those are essentially just hidden attributes inside of your geometry, which you can visualize if you go into geometry spreadsheet, click on the primitive button, and then here in the intrinsics dropdown, we can click on packed full transform. Where is it? Packed full transform. And this is essentially just a transform matrix, right? A transformation matrix which has translations, rotation, shear, and scaling. So if we scroll through here, we can see that we have all these numbers animating. Not all too important if you're just doing, animations in Houdini and you want to export it, but that is the data that the tool I'm going to be showing next uses to export this animation we have to Unreal. This animation we have to Unreal through FBX. So to export this, first we're going to create a ROP network, because the RBD to FBX tool lives inside of ROP's context. Okay, type inside, and then we just type RBD to FBX. Okay, so there's a couple of things we need to set here. For this example, since it's just easy, we just need to set which object we want to export. So I'm going to select this node, hit Control-C, and then in here, hit Control-V, and that will give us the path here. We can also click this drop-down, but that would require me to scroll through a list, and I don't like that. So I'm just going to use it like that. And next up, I am going to set the uniform scale to 100, because once again, we're going from Houdini to Unreal, we're going from meters to centimeters, and then that's all we really need to do. Unless, of course, you want to add some additional transforms. At the start and end frame range, 1 to 200, that is perfectly fine, because that's the complete frame range we have animation on. And then all we do is just hit render, and that is going to show us an export dialog and export everything to disk. There we go. And then as soon as that's done, it will give us an FBX. So what is this process doing? What is this tool doing? This tool is essentially internally doing the exact same thing that the static fracture export is doing. It is creating a unique geometry node per packed fragment. And then on the object level, it is going to apply the transforms that were stored on the primitive intrinsics on the object level parameters, right? Because once again, everything that goes into a game engine typically needs to be bone-based, okay? Let's just wait for that to finish. And there we go, we have our FBX. So let's go inside of Unreal and hope that it imports it properly. Let's delete all these guys. Hit delete. And drag this guy in. So the difference between this example and the previous one on the Unreal Engine side is that this will give us a somewhat different import dialog. First of all, the biggest difference is this mesh section. This will now show us that it's a skeletal mesh, meaning that we have bones inside of our FBX. So the import settings, important, enable skeletal mesh, import mesh needs to be on as well. But skeleton needs to be empty if this is the first time that you're importing something, right? This will essentially trigger Unreal to create a new a physics object and rig inside of here to apply the animation on. The next new thing we'll see here, if you scroll down, is the animation tab. We need to enable import animations, right? Because we want to import the RBD simulation we just had. And for the animation length, we can just keep it to default, which is exported time. The other two options that are there is animated time. So this one essentially allows you to only import the frame range that actually has animation. So let's say we exported a frame range of 200 frames in Houdini, but the simulation ended at, let's say, 150. It would only import 1 to 150. And then set range allows us to decide which frame range we want to import. For example, we want to import only frame range 10 to 50, and then that we could use this setting. But for us, for now, we could just keep it to export setting, exported time. Let's see, is there anything else here? We don't need to set import uniform scale because I already did that in Unreal. And then last but not least, make sure that you have convert scene on, because otherwise we'll get a weird orientation. Hit import and Unreal will import our file into the engine. Do we have any questions in the meanwhile, Mike? No, I don't think so. Okay, then we just once again drag and drop our geometry into the game engine, and then to prove that it indeed does hold animation, we can click and drag here on this parameter called initial position, and this will allow us to play the animation in the viewport without having to create like an animation tree or a blueprint that will play this animation. So this is a really great way of just visualizing whether or not you indeed did get your proper animation. Okay, so that is RBD to FBX export. We did make some changes recently to this tool. So if, for example, you had any geometry that does not hold any animation next to it, for example, like a box or something like that, it would filter out that for you, right? It would only keep the animation. So that's a gotcha with the RBD to FBX node. Okay, so that was that. If you have any questions about this, feel free to reach out. Let's go to the next example, and that is going to be Pivot Painter. So Pivot Painter is a tool that allows you to store pivot information per submesh in the vertex information of the geometry. So for example, if you have a sphere with boxes sticking out of it, which is the example I'll be using, we can store for every single box where the pivot is. Let me just go to that example. And there we go, and go to geometry. There we go. So let's say we have this, right? And we want to add animation or some sort of motion to every single box on this sphere. We could either, do a simulation or manually animate these inside of Houdini. But if we want this to be more interactive or, for example, be modified based on a player that walks against it and so forth, we could do that with a shader as well, because it's pretty simplistic type of animation Instead of making bones for that, we can use Pivot Painter for that. So there's two things you need for Pivot Painter. We need our geometry, and we also need our points, okay? These points will function as the pivots. So for every single box, I have a point which resembles the pivot location of that object that I'm going to encode in the vertex colors. And there's a tutorial online that shows exactly how to set everything up. I'm just going to show you the import settings for Unreal. Then once we have that, we plug it both into Unreal Pivot Painter, and that is going to give us something really cool looking. Looks great with these colors, looks awesome. This essentially just stores the pivot information. So if we look at it from above, we can actually see that the colors sort of match the axes inside of Houdini. Okay. Then once again, let's do FBX export. Plug everything in. We can keep these as default settings and hit save to disk. And that will give us our FBX on disk once again. Let's go to Pivot Painter. There we go, out. So, since I've opened the content example project in Unreal, we can actually use the shaders that Epic provided to use with Houdini's Pivot Painter. So to get those, what I like doing is just going to this maps folder and going inside, scrolling all the way down, and then opening the map called Pivot Painter. Just double click that, and it is going to load it up for you. We don't need to save any of the other stuff. And then when we open it, we'll get this scene that we see here. And the example that I just made is one of the examples that is provided here inside of Unreal, right? So there we go. We have this star sphere looking thing with per individual box, right? So I'm going to import my FBX that I had, drag that in here. And then with this tool, the import settings are really important. So if you go to Google and you type Pivot Painter Houdini, we'll find the tutorial that I made, which also shows the import settings. So all the way at the top of this page, we can see that since version 1.27 of the toolset, which is a really, really long time ago, I think we're at 205 or something by now, the import settings have changed for Unreal. not because something changed inside of Houdini, but because of some changes inside of Unreal itself. So if you scroll all the way to the bottom, I made a screenshot of the exact settings we need. So the important one is vertex colors, set that to replace, and also convert scene needs to be on once again, but also generate light map UVs needs to be turned off. The reason for this is that Pivot Painter uses UV information to store the pivot locations and lots more data like that. Let's import. Okay. And then we can just drag and drop this guy in here, but as we can see, it does not have any animation yet. So we can just click on one of these guys, grab its shader by clicking the final glass there, and drag and drop that onto our geometry. And voila, we now have that same animation Unreal. Well, that seemed pretty easy, right? But there's a couple of gotchas that you need to keep in mind when working with Pivot Painter. Even though the example I just showed you works, if we, for example, grab this guy's shader, which rotates around its axis, and apply that to our example, we'll see that it will actually bug out. And this is something that people often report as, the tool doesn't work, but there's actually a gotcha inside of Houdini that the tool needs for it to properly work. First of all, I'm going to disable layout light map UVs. You can keep it on. I'm just doing this to save some time because otherwise it would have to compute it. The reason it's acting out weird is because we don't have UVs on our geometry, okay? Because for proper orientation and direction, the tool needs UVs. If we click on it and scroll down, you can see that it uses UVs for pivot position. So now that we do have UVs, if we go to spacebar 5, we can see that it indeed generated UVs for us, then it will work properly. The other thing that we need to keep in mind is our geometry that we export to Unreal already needs to be in Unreal Engine units inside of Houdini before we export it, okay? So if inside of Unreal we were to change the import uniform scale to 100, the information that we are encoding into our vertices will not match anymore, right? Because if we click on our Pivot Painter and go into Spreadsheet, these numbers, like for example the vertex colors, if you import in Unreal times 100, these values which specify pivot location do not get multiplied by 100. So that's where a mismatch would happen and you'd get really weird results. However, since we multiply our object with a scale of 100 before encoding it, right? So in Unreal scale it will be encoded, then it will work perfectly fine. So now that we have UVs, let's export it out once again. Save that to disk. There we have it, out 2. We can now import that into Unreal again. I just hide this, hit import. We can delete this guy because it's incorrect. Drag this guy back in. Take that same shader that was filling before and assign that to our geometry. And now, voila, we can see that indeed the orientation and the positions are all correct when we apply this animation. The weird shader results you see here has nothing to do with the animation itself. That's just because of the UVs. They're different from this object. Okay, so that's the example I have to show for Pivot Painter. Let's now look at another example. Let's go to animation, bone-based animation. Let's hit open, go to animation export, and open our skinning converter example. All right, so I did a quick cloth simulation. This is the scene file that you can find on GitHub. Oh, I see there's a question that came up about Pivot Painter. Yes, so the reason that the tool is specifically for Unreal is because Unreal ships with material functions that give you all the information or extract it in a proper way. So if inside of Unreal, inside of a material graph, you right-click and type Pivot Painter, you will get this node here, which has all this information that the Houdini pivot painter encoded. For example, x-axis vector or pivot position, random values, alpha, object scale, black mask, etc. If we dive inside here, we can see that all this really does is just grab the UV values, does some math to it, and then export that as a pivot position. Same goes with the other things. So for example, it uses the vertex colors to create a black mask. So if there's no vertex colors, it would not have any motion, the object scale, and random values per element. So this is all just simple attributes that Houdini encodes in the right way so that Unreal can read it as pivot painter information. The tool inside of Houdini is called Unreal Engine Pivot Painter. If we go here, GameDev Unreal Engine Pivot Painter, just because Unreal ships with that specific material function that decodes the information that this node exports. You can, however, also use this inside of Unity, but you'd need to replicate the shader that we see here inside of Unreal, which is a pretty easy task, but it's just something that's a lot easier in Unreal because they ship with it. So that's why it's called Unreal Engine Pivot Painter instead of Houdini. I hope that answers the question. Yeah, I was going to show you animation. So I did a cloth sim in Houdini with the old cloth solver. I did not use Vellum because I'm just using the example that was made before Vellum was released. This is the HIP file that you can find on GitHub. So you can use the exact same HIP file I'm using right now to replicate what I'm doing. Let's use the scaling converter to convert our vertex-based animation, right? If we enable our point visualizer here, we can see that every single point has animation attached to it, which we can also confirm if we go to the points tab and look at the position values. As you can see, there's no packed full transforms here, meaning that it is indeed a point-based animation. So Unreal or any other game engine needs a bone-based animation. And the scaling converter is going to give you a bone-based animation from a point-based animation. So what we need to do is just cache out our file to disk. I already have that, so that's why we have smooth playback, and plug it into the primary input of the tool. Like you see, it says deforming mesh sequence. The second input takes additional bone positions, and the third one takes additional animation. Once again, we have a tutorial covering all of the parameters on how to exactly use this tool online, so I won't go into too much depth, but basically what we need to do is just specify how many bones we want. I'm just going to keep it at 100 because that I know that's going to give us a pretty decent result, and set the frame range to bake. In this case, my animation has 50 frames, so I'm going to 50. I'll click Convert to Bones, and that will bring us this pop-up window on Windows. It's going to generate a skeleton and then bake the skeleton, keyframe everything, and then it also still needs to do the generation of the weights for all the bones. So while it's doing that, we can see that it has created an output object at the object level called scaling conversion Geo1, which is the name of this object, with 100 bones. So if we close this and go up one level, we can see that we now have this subnetwork similar to how we've exported our previous FBXs, right? The static geometry, but also the packed primitive exports. So if we dive inside, we'll find something new. If we press L, it's going to rearrange our network to lay everything out. If we zoom in, we can see that we have a lot of bones, right? There's one bone per sphere that we saw in the vertex or the scaling converter previously in SOPs. So if we click on these, we can see that every single bone has keyframed animations on its translate, rotate, and scale parameters, okay? And that is the data that is driving this piece of geometry now. So to prove that to you, I'm going inside of this geometry node because that's what the bones are skinned to or attached to. And we'll find our object merge. We'll see that The object merge literally just imports the geometry that we plugged into the skinning converter, which still has our point-based animations. Below it, however, we have a time shift, and this time shift is set to the start frame of whatever you just wanted to export using the skinning converter. In wireframe or in ghost mode, we can still see these little bones, right, that are animating. So those are holding the actual animation values. So one way of skinning things in Houdini is using bone biharmonic capturing. And for that, you'll need a bone capture lines. And what that does is essentially just creates these little capture lines per bone, right? So it creates that sort of spine for that bone. And then it plugs into a solid embed node, which is a cool node. I don't have time to explain it. But then afterwards, with the bone capture biharmonic, it will attach the attributes that it generated here, right? So which bones go where and which points are affected by the movement of those bones to that object. And then last but not least, we have this deform node. And this deform node is going to use these capture attributes that bone capture biharmonic generated to deform our object. So now if we play, once again, we have our object being animated, not by the original point animation that was stored on here, but by the little bones that are flying through the scene, holding the animation that we generated using the skinning converter. If you want to export animation using Houdini through FBX with bones, it is important that the very last node in your geometry container is this deform node. Don't put a null behind it saying out or else. No, deform needs to be the absolute last node. Even if you bypass this node, it will still fail on export. So make sure deform is the very last node with the display flag set, and that will give you the correct result. So to export that, select our skinning converter subnet that we generated. Either, once again, go to the ROP context to create an FBX export, or let's show you the other way. Here in the file menu under export, we can click Filmbox FBX, select the location that we want to export at. So let's say out1.fbx, and then let's export our frame range. We want to export a range 1 to 50 because that's where we have animation. And then we don't want to export the box, but we want to export not the bones holding animation, not the geometry holding the geometry, not the root object is null. No, we want to export the subnet containing everything inside of it, right? This is the parent. So set that, and then we can disable export and effectors. There's always a conversation about the difference between bones and joints. The only thing you really need to know is if you want to import a clean rig or skeleton inside of a game engine, disable export end effectors. That will reduce the number of bones it generates. Hit export, and Houdini will export our frames to disk. And then inside of Unreal, let's not save that. We can now import our FBX. Drag that in there. And then once again, we'll get that same dialog we had before. But remember what I said, if you're importing a new skeleton, right, make sure that skeleton is empty because that forces Unreal to import or generate a new skeleton for it. Make sure import animations is turned on, export time is fine, and convert scene is turned on. I also want to import my, I'll change my import scale to 100 and import that inside of Unreal. Just wait for that to finish. And then once again, similar to the RBD to FBX example, we'll get a skeletal mesh, we'll get an animation, we'll get a physics object, and the skeleton itself. So let's find our cloth simulation. There it is. To once again preview the animation, just drag and drop this object, the one with the green underline, which is the animation sequence, into the viewport, and then just scrub with this parameter, and voila, we indeed do get our animation from Houdini inside of the engine. Okay, let's take a look at the skeleton for it. Out one skeleton, if we click on our animation here, we can see all the different objects it generated. And here we have all the separate bones. There we go. We do indeed have 100 bones, just like we specified in the physics painter object. Okay, one last thing I also want to tell you about, if you want to stay up to date on changes that are happening in FBX, because it's a continuous process, you can go to the side effects website, and then under support, you can click on changelog/journal. And then we can set the category, if we scroll down to FBX, hit submit, and that will only show us all the FBX changes that are happening inside of Houdini. So we can see the last one is September 5th, which added some new features. For example, the or improvement behavior for importing and exporting materials. Yeah, that's everything I have to show. Let's go to some questions. Okay, so a question that came up is why does exporting objects with expressions on it not work properly with information? So, for example, we have a box, and we were to use translate with $F. We do indeed get hello. Let's try it here. Okay, so let's say something's animated like this, right? But then on a transform. Let's actually use a transform node, and then say $F. Okay. So why would an animation like this not export? The reason for that is because this is an expression and not a baked keyframe, right? As you can see, if we select this node, there are no keyframes here. So in order for this to work, we would need to bake this expression to keyframes. Or use chops in that case. Any other questions? Okay, so another question is, which is better for simple cloth simulation, exporting as vertex animation or bones? In terms of overhead, for an engine like, for example, Unreal, vertex animation textures is a lot cheaper because it's all just shader driven, and the shader for vertex animation textures is really lightweight. But the limitation there is you can't really modify that animation like you can with bones. Well, what do I mean with that? If you have bones inside of Unreal, we can actually apply additional simulation inside of Unreal. So as you saw before, it also generated this physics object. The physics colliders are a bit wrong, they're incorrectly scaled here. But with this, we can, for example, add collision with the player if they walk against this collider. That is something that you cannot do with a shader, because the shader has no idea of where the player is, unless, of course, you code it in. But in general, if you just want to play an animation without any sort of interactivity, use vertex animation textures. Otherwise, use bones. Another benefit of using vertex animation textures is that your animation will be exported at a higher precision, because you're exporting a point-based animation, meaning that every single vertex has information data rather than every single vertex being driven by a bone, right? The bone is basically just calculating an average of the motion of a number of vertices and then driving those together. So for some engines, bones is better, but that's typically just for proprietary engines because they have very specific requirements. Another benefit of using bones, however, is that it allows you to attach sockets. So since we saw all these bones here, we can just right-click and say Add Socket, And now that we have a socket, this socket will also be animated, right? You see it moves with the bone. This allows us to, for example, attach all the sorts of effects during runtime. Like, for example, attach a particle effect to this socket, or a gun, a sword, or anything else like that. The next question, if any. Those are the questions. All right. If there's any other follow-up questions, feel free to send them to our office hour Discord, and we'll read them there. If you have any suggestions for topics for the next stream, or if you have any problems you run into or you'd like to do as an example file, send this to us right there in that channel. All right, that's it for this stream. Thank you, everyone, for showing up and listening. I hope it was useful. And once again, sorry for the technical difficulties.